All right, today we're going to talk about binary digits or bits, which is just an abbreviated version of binary digits. To understand binary digits, we need to understand that there are factors of 2. 2 to the 0th power, 2 to the 1 power, 2nd power, 3rd power, 4th power, 5th power, 6th power. And that's how we're going to convert this binary number into a decimal number. This is how we understand our numbers today based on powers of 10. We have 0, and we have 10, which is 10 times, and then we have 100, which is 10 times, 10 times 10. So with every new digit we create, we increase in a factor of 10. But with the binary digits, it's a factor of 2. So 2 to the 0th power is 1. 2 to the 1st power is just 2 times 1 is 1. 2 to the 2nd power is 2 times 2, that's 4. 2 to the 3rd power is 2 times 2 times 2, which becomes 8. We notice that we're just multiplying each number by 2. 8 times 2 is 16, times 2 is 32, times 2 is 64. So we keep this in mind as we are converting binary numbers to decimal numbers. So this binary number 100100 is just activating the factors wherever the ones are. The zeros remain blank. So we work from right to left with binary, so it goes 0, 0, 1, 0, 0, 1. And then this 0 here is implied, but we could put it at the beginning here too if we so choose. See how it just kind of removes. So as we use these ones, we use them to activate that power. So this 1 here in the 1, 2, 3, 4, 5, 6 position over is 2 to the 5th. And so we have 32. Then 0 plus 0 plus this 1 in the 2 to the 2nd column, so that's plus 4, 0, 0. We can put those zeros in. And so we have here that 32 plus 4 equals 36. So we can understand the binary number 100100 equals our 36. Likewise, if we want to reverse it, say we have a decimal number of 50, how do we turn that into binary? By going in reverse. Can we use a 2 to the 6th power, 64? No, because that's too large. So we'll put a 0 there because we don't want to activate that. 32 counts, so we have 32, but then we have to subtract that out of the total. So we have 50 out of 32, which is, can I do the math on here? 18, which means we can activate the 16. So we put a 1 there, and then we have 18 minus 16, that equals 2, which means we don't need to activate the 8 with a 0, we don't need to activate the 4, we do need to activate that 2, and we don't need to activate the 1. But could we add the 1 twice because we have 2? Well, we can't do that because it's either activated or not. So to be 50 would mean that the binary number is 0110010. And that is how we can calculate the difference between binary numbers and decimal numbers. Moving forward, we're going to talk about how we can accept binary, how computers accept binary and show us text or numbers like you see here, or pictures or audio files. Because all the computers can understand in some cases is the binary numbers, the machine language that then gets translated or interpreted to what we can see or what we can hear. So stay tuned for that in part 2. Thank you. Today we're going to continue talking about binary digits and how they correspond to symbols that you and I see. In a text editor like Google Docs or Microsoft Word, we might type a number or a letter or a symbol and we will see the symbol itself. Let me find them. But the computer will see or have to use binary numbers to navigate all of this language, which is why A is 0, 1, 0, 0, 0, 1. That's 1, this is 2, this is 3, 4, 5, 6, 7. Because if you remember our powers of 2, that's 1, 2, plus 1, 1, plus 1, 2, plus 1, 4 equals 7, 8, this is 9, etc., all the way down. Plus this 1 over here, 1, 2, 4, 8, 16, 32, 64, so 64, 64 plus 1, 64 plus 2, 64 plus 4, 64 plus 5, etc., etc., etc. And this is the ASCII, which is the American Standard Code for Information Interchange, which is a common language used by computers. Then, as we get into emojis and symbols on our phone, they're also represented by a different binary number. Now, I want to point out this PowerPoint by Peter Mathis for the Engineering and Computer and Electricity Department in Colorado University. When we have a black and white image, say of a house on a 9x13 grid, it's either white, not activated, or black, activated. And it could look like this, where the ones are the activated cells. And so a computer could store this with the ones and the zeros, and that would require 117 bits. When we add the color red, now we have to use 2 digits because it's no longer zeros or ones, but we have to add a 2 for the red, which then can be seen like this, which means we need to double the amount of digits stored, 117 to 234, 9 times 13 times 2, so now we have 234 bits because it has to be twice as big. This is a problem when we have to figure out how to read this, because it could either be 1011 or 10110 or 10110 10110, and we need to be able to figure that out. So computers are able to parse apart the pixels, and when we add more colors, we have to have more bits, which is more pixels and more data, which is why when we have computers or monitors, we look for high definition, which is the most amount of pixels, which could then translate to the more amount of definition for the more amount of data or binary digits being translated. To assist with all of this data being processed, there is a lossless compression, which means there's no loss in data. But a person by the name of Huffman has included short code words and frequent colors to make code word strings unambiguous. And he makes a tree like this. So 0 is white, 111 is blue, 110 is red, 101, 100 is green, 101 is black. And so we can compress that to look like this. And that only requires 56% of what it was before. So that is just a brief rundown of how binary digits can get interpreted by computers and how what we see is not what the computer knows. Thanks to Peter Mathis and Colorado University for posting this online. Thanks to ASCIIcode.com as well as ASCIItable.com. Thanks so much. Bye.
Hey everyone, thanks for sticking around. If you're interested in more videos, you can click here or here. If you're interested in subscribing to my channel, you can click here. And if you're interested in seeing any other students' work, you can click here. Thank you so much. Don't forget to like and subscribe.